A connected graph that has a cut vertex has the property that if I remove one particular vertex, the graph is now disconnected. And thus, in spite of the book not using it. A graph is non-separable, no cut vertex. More can remove more stuff. Consists of a single vertex, then a graph that's with a single vertex. But it consists of more than one vertex, and I take more things to get this graph disconnected. And then the size of the vertex, how connected the graph was to start with. Well, to that end, I'm going to define a minimum vertex cut. And it is possible to have more than one vertex cut. You might be able to take away two more than one way to disconnect your set. That's a vertex cut. Cardinality. If you have a graph, let's assume for what does it mean if I tell you my graph is a graph? There's one pair that are not adjacent. There are two, so that the edge between them is part. Okay. If I let my set U be all of the vertices except 2. When other vertex except vertex. Look like. Away everything else except two isolated vertices with no edges. However, if I have a complete graph and I take away x, everything else is still connected to everything left, isn't it? As a matter of fact, if G is complete, G minus U always still. Consider you have a graph that is 5 vertices. Take away. If I take, I'm left with these connected to each other to begin with. If you take 1, the remaining 4 are also connected. If you take away 2, the remaining 3 are all. No matter how many you take away, the graph is still complete, and therefore connected. It's proved. Every graph that's not complete has a vertex. Even if it's you guys that weren't adjacent, take away enough to disconnect this graph. Okay. So let me think about a graph that's vertices in this set. This again, English, the is twitchy. I would have said incomplete graph G, complete. Non-complete graph G, I have a minimum vertex cut. Then G minus U is disconnected. Well, that means there are components minus U. I don't know how many. So G2 to GK. All right, wait a minute. So the whole graph minus cut U has pieces. There. And then there are these other vertices. U. Doesn't matter. this vertex, right, call it U1. What is the minimum of things that vertex has to be? What's the minimum degree of U1? Why 2? Suppose it just connected the, right? But then that somewhere, since there's no other way to get from here, if I left U1, these two would still be connected, wouldn't they? That would be one component. Right? But that would mean if I removed everything, I'd still have a disconnected graph. That's exactly. It was a minimum cut. That has to be connected to every one of the components. Because it was only connected to 2 of them, it's still disconnected, left out that vertex. It's got every one of those. I be connected every of G sub J. J goes 1 to K. Otherwise, I'd have a vertex terminology. I like this idea. If the minimum number of things that connected every other part piece. Go back to our box from last Friday. We had 3, right? And they were all cut. If I removed any one of them, disconnected. Right? The different numbers of pieces depending on which one I remove. The activity of curly K of G. The size a minimum any minimum vertex cut. We'll remember the right term. Now it is possible that G is trivial. I take all myself one lone vertex. connected, isn't it? With one vertex, technically. So let me. G minus U is I just said that's really lame. What do you think of that number, G? All I know about my graph is it's connected, right? Zero. I don't need to take any of these away to get a disconnection. I have to take away all the vertices except half that gets. That's the biggest possible thing. I'd have an empty set. That's a blank page. If it's zero, if it's one, vertex. If it's two or more, my graph is not full, and it's got at least three. So let's look at examples. That thing at the start of page 7 started. Here are my examples. All of these none have K of 0. Which of them have K of 1? Asking you 1 is the same as that vertex. Vertex. Every vertex, vertices are cut vertices. G2 bridge, the ends of the bridge are cut vertices. Central vertex is drop it out. That means that G4 through G7 activity number. Think about G4 cycle. How many vertices does it take to take apart? Take any two already adjacent, split off a top and a bottom, a left half and a right half. What about G5? When can I take away? I claim it's 2. These, but then the result will still be connected by that. lone vertex, it would leave the lone vertex on the top. So I can do it. The Harari graph here. Now, if I remember, vertices, each thing is regular. That's H74. I don't remember which one. I want to distance every single thing is connected to 4 others. So if I pick this vertex at the top, 4 things it's connected to, the top vertex and the bottom. It's empty. I got nothing. That takes me on because that's a complete graph. Everything except one vertex. So it takes 4 for this middle graph. We decided on. 4 connected. You remove a set of at least 2 connected. To disconnect it, I need to remove at least 2. And a minimal connectivity setting. Now, if my is reconnected, I move 3 reconnected. Also, it can't be divided by 2 if it's by 1. But it can't be disconnected. So if it's connected, it's also 1 connected. So it's also connected. So far, so good. What do I need to pull out to make this thing disconnect? If I can do it for edges. Now remember, when you remove a vertex, the edges that are connected to it. When you remove an edge, your graph contains an vertex. You can do an edge cut of +1 to disconnect. Take away the one edge. Every tree has an edge of size 1. every has a bridge, has a cut of bridge out. That's the definition of bridge. If you remove the edge of the bridge, you get the graph. Oh, okay. Between vertex cuts, minimum edge cut, minimum vertex cut. The vertex cut plus number of vertices I get. I don't have a minimum edge cut. I have a minimal. Different. This says no proper subset of thing I am currently looking at is also. There may be a complete difference that has, but this set is minimal if you need all those to cut it. If X is a minimal edge cut, then G minus X contains the auxiliary component. Only two. And that means if I remove a tile on one side of Pittsburgh, across the same day, I have to take away all the bridges to disconnect the river from the other. But I haven't changed the number of sides to the river. I've only taken away the of grass. Even if technically the bridge, let's say I had vertex of degree 2 and I took away the vertex of degree 3. 2 edges that went to the other side. You get rid of it. I have only 2 components, G1 and G2, and contain all the edges. A vertex to vertex in G, and vice versa. Full edge cut of all possible, a minimum. Here's a graph. Here are edge cuts. X2. My question to you, which is in a mole are any? One, out all three of those edges. The way this connects it to P3. If you took away two of those, it would still be connected. So that's no proper subset edge cut. Two takes one and vertical edge that is easy with the L shape. But if I only take away edge, it's still disconnected. So while this is an edge cut, null subset connects. Why? Would you disconnect? This. It's got three bridges, none of them. Not physical bridges, gravity bridges. Okay. K of G vertex cut here. The two in the middle work really well. But I just came up with that K of G. K of G is the minimum. The edge L lambda is the minimum number you take away. And that's true. Could be zero. If it is already disconnected, must it be less than or equal to n? in a tree, and I could have as many edges here, but that's actually a helpful. Most connected I could get if everything was connected. Vertex 3 minus 1. This one edge is all from the same vertex. Oh no, disconnected from everything else. So even in the most graph I've got, complete graph, I can just have one vertex. But if the graph had no vertex cut, right? As long as you vertices, it stayed connected. But in any incomplete graph, minimum edge cut in what graph is the possible edge cut. Degree, and I remove all the disconnected. Connected, I have one edge isolated out here on the side. I never need that number to be big degree. Full graph, not a multi-graph, not a vertex connectivity smaller, the connectivity is smaller, equal to the minimum possible degree. I wrote theorem. Read the proof. I don't want to do it. Not all that. It's just about a page and a half, and I've only got, and I don't want to do it. It's a page. Where they're different. I take one vertex, right? On two sides by things, you take away two edges. These two, and side or vertices. They can, I think they can all be equal. The most common type of activities are equal. If I graph three, then that its vertex connectivity and its edge, what they both are. If my then I can remove three to one vertex and disconnect. So the edge connectivity is three. If I take away three, let's take the three adjacent. We take away those. Leave this one vertex. My graph. But that turns out to, regardless of any other problem, if my every three, activity is three, and the vertex is two. In general. Suppose n and size. Well, then if I tell you you have n minus one edges. N minus one. You have n vertices, n minus one edges. Connected. What graph are you? Which means one cycle floating around there somewhere. Oops. That's true. degree means the average is 2 degree is equal to that. And I know it takes fewer than that. Minimum edge connectivity and like that doesn't require anything other than averages. Bound is strict. This is a strict relation. You can whose connectivity is that number. Connectivity is exact. All right. This is to actually start with any graph. A connected graph. What's the graph? Sorry. Graph the diameter means something. That's the length of a G from diameter, small distance. It's the large G. Here's a 4 1 less than or equal to A less than or equal to D 9 G to the K. Of G to the K is the vertex set of G. And UV is in of G if one the distance in V less than K. Vertices new edges up to that is absolutely absurd. I'm going to start with an example. I'm going to do squared. P6 pick a vertex connecting to 1 or 2. That's here. Top. I squared and sees apart. See here, those are all the vertices. distance to is 5. Has power. And are the Harari graph. Exactly the graph. Of that so many is exactly Bill powers. The 2 up. I'm going to on this in the next session, but that's going to take more than one day. You should read the example which generalizes this further. Friday. Me. See you all at the time of that.